Hello everyone, welcome back to another video from F215. In this video, we shall be discussing the concept of principle of deformation of contours. Principle of deformation of contours. Okay, big title, but a relatively simple concept once you get the hang of it. So, in a previous example video, you were asked to integrate the following integral: 1 upon z dz, and I use the concept of parametrization to solve it, where our contour C was 2 e to the power I theta, okay, or the parameterization, so to speak, was z of t is equals to 2 e to the power I t, where t varied from 0 to pi. Okay, now the thing is, let me draw it again. The contours. Okay, here's your contour, which encompasses the sort of discontinuity, right? Inside x and then y. Okay? Say I gave you a different structure, but it's still a closed contour. I gave you a different structure. Okay? Say I gave you this structure. X, y, and I gave you this structure. Let me draw it much better way. Let me draw it better. Okay, you have the square, and in between you have the apparent discontinuity at z is equals to 0, right? Okay, now this, where our contour was 2 to the power I t, gave us the value of our integral to be 2 pi. Okay, I'll just write it here. For this, we got the value of our integral to be 2 pi pi. Okay, what would be the value of the integral given the contour was like this? So of course, anti-clockwise again. What would the value if we were to have it like this? Now, before that, let me introduce you to the concept of principle of deformation of contours. Okay, so if you have, say, contour C1, okay, let me denote a contour C1, and interior to this contour is another contour C2, okay, positively simply oriented, both of them. Now, C1, if we have these kind of structures where we have one contour inside another contour, or more contours inside other contours, if C1 and C2 are closed contours with C2 completely inside C1, and a very important fact, the fact that the function f of z is analytic at this sort of on the contour, as in not inside the contour, on the contour C1, it's analytic on the contour, as in on this, basically this line, this sort of circular, the edges of this sort of contour C2, and it's analytic in this sort of region inside. Nothing is said about in the inside of the contour C2, but what we know for these conditions to match and to use clever ways of finding out values of integrals is that the function has to be analytic on this contour, not inside, on the contour C2, not inside, and here, now I'm going to say inside C1, but not inside C2. Okay? So in between these boundaries, the function is analytic and continuous. Okay? So given all these, let me write it. Officially, f is analytic on both C1 and C2, and at each point interior to C1 and exterior to C2. Okay? If these conditions are met, then you can write this following statement. We erase this part. Alright. Then and only then, hopefully you have that image in mind. You've drawn it in your copy. If you haven't, please rewind the video, draw it in your copy because that's going to be used as well. I'm unfortunately lacking in board space. Okay. So if all of these are ring true, then this holds true. Integral of f of z with the closed contour C1 is equal to the integral f of z dz with the closed contour which is interior to C1, C2. Okay? These statements are, both of these things are equal to each other. Okay, so given this is your mega structure C1, okay? You can take any contour inside this or this, whatever. Let me keep it as a circle and we'll see. Okay? We know the discontinuity occurs at the origin, as in when z is equals to 0. So we can have a smaller circle, which is inside our contour C1. We know this is C2, and this contains our discontinuity. But since the integral of C1, which we evaluated previously, gave us 2 pi I, and because this sort of structure follows all the necessary conditions for this to be valid, we can state that the smaller integral will also give us those integral around the smaller contour C2 will also give us 2 pi I. And so why did I do this? So that I can draw another small little circle inside here. Okay? A small little circle inside here. You can denote this you can have this be a smaller circle. Okay? Take this to be the contour C, okay, or directly write the parameterization. Z is equal to, say, for example, half e to the power I t. Okay, so I'm saying it's half because the structures are relatively similar, as in the diameter of this circle is what? The radius is 2, so the diameter is 4, and in similar fashion, the lengths of these sides are 4. So if you take a smaller sort of contour circle, this is C1, okay, and we have C2, is also positively oriented, as in the anti-clockwise direction. So if you take a smaller circle, half e to the power it, and if you do the parameterization, the integral in the same way we parameterized before, you will again get this sort of smaller structure to be equals to 2 pi I, and of course these two contours maintain these two stipulations. So the integral around C1 would also yield you 2 pi I, as in integral of C1 of f of z, 1 over z dz will also yield you 2 pi I. Okay? So this is how you use these two contours in the principle of deformation. Now let's delve a little deeper. And this would add as a precursor to the following concept known as multiply connected domains. Okay? Okay. Now, those were deleted neighborhoods, and so you can claim them to be simply connected domains. Okay. Now let's work with problematic domains which are not simply connected. Okay. So given your domain, this is your big domain D. Okay, whatever structure it has, and you have a contour C1 going like this, and inside you have another contour. Here it's C1, inside it's C2, of course oriented in the anti-clockwise direction, but it unfortunately has a hole inside this contour. Of course, simply connected domains cannot have contours which have holes inside these domains, so unfortunately they have holes in them, so we cannot claim them to be simply connected domains. But however, we can change the nature of these contours and make them to be simply connected. How do we do that? Like, let's extend a line segment which connects this contour to this contour. Okay? And we denote this new sort of contour, this whole contour which contains this contour as well, as C prime. Okay? And okay, let me draw it separately, keeping this intact. Okay? Gaze your eyes here. Hopefully I can keep the structure intact. Now, these are meant to be the same diagrams, okay? So please bear with me because I'm a very bad artist. Now, how do we connect? How do we make these into simply connected domains? Extend the line segment, okay? This originally, which was C1, okay, keep this as anti-clockwise and extend a line segment from here to here in the contour that's sort of creating your problem, okay? Since previously you could evaluate them using the concept of simply connected domains, but here you have to do some wiggling around. Okay, connect a sort of bridge, or I'll call it line segment officially, but I'll call it a bridge. You'll know why. And then this bridge contour goes from here, here, and then comes to our bridge, and then enters our new contour here. As it enters our new contour here, it enters through here, and then exits. It enters through here, and then exits out again through here. Okay? Exits out through here, and then moves around again. And that is your crater structure C prime. Okay? What you're doing here is you're completely negating this small part which contains the whole. Okay? So what you're trying to evaluate, yeah? What you're trying to evaluate here is basically, what you've created here is a simply connected domain, because as you can see, inside this domain, the contour is made in such a manner such that it has like a donut-like hole inside it, where we don't have any contours. Okay, so of course now it has become analytic. So you can see, yeah, it has become analytic, right? Now, by Cauchy-Broussard theorem, this C prime is a new curve that traces around C1 and then via bridges crosses C2 and then back into C1 via the bridge again. Okay? So let's try and do some calculations with it. Since we have the fact that C1, remember this is C1, this is C2, okay? C1, oh, okay, let me write it again. Now that it is simply connected, now that the form is simply connected, we can state, according to Cauchy-Broussard theorem, C prime, as in the overarching newly modified contour, C prime f of z dz is equals to 0. But we must break it down, right? Because there are quite a few substructures inside C prime. So first off, we have C1 f of z dz. Okay, but then we have a bridge, right? From C1, it goes and enters this bridge, but the orientation remains similar. So we have plus the bridge. Okay, do you know the bridge is? Okay, let's just let me write bridge. B-R-I-D-G-E. Bridge, which is basically this line segment going from here and then this bridge. Okay, and then f of z dz minus. Since C2 is not oriented in the anti-clockwise direction, it's oriented in the clockwise direction. So we have to now introduce a minus sign since it's going against our notation of what positive is in our integrals. So we have minus f of z dz. Here we have C2 plus, since it's made its rotation clockwise, it has to leave the bridge again and join C1 again. So since it leaves the bridge and it leaves it in the notation which is opposite to the original notation that is defined, we have to introduce another minus sign. Okay, so minus, there is bridge f of z dz. Okay, and this whole thing is equals to 0, right? This whole thing is equal to 0. You can cancel out the bridges because they're basically the same structure, it's the same line segment, just coming in and then going up. So they're negating each other. You cancel out the bridges, okay? But what you can't cancel out are these two contours because they're two fundamentally different contours. So what will happen is you can take this contour on the right hand side because right hand side is basically 0, and you're simply proving the original statement that I stated before in regards to deformations of contours, principle of deformation of contours, the fact that integral of C1 f of z is equal to the integral of contour around contour C2 f of z dz. Okay? So you've proved this. Now let's do some problems. Show you an example. You're asked to find out the value of this integral, z plus I dz, where C is the square with vertices. The following vertices, I will not write it here and then write it here again. I'm going to draw it. It's a square. Okay? Our vertices are 2 plus 2i, 2 minus 2 plus 2i. Here we have minus 2 minus 2i. At this point, the edges. Here we have 2 minus 2i. Okay? The vertices, and we're asked to find out what is the value of this integral, right? Now, simply using the square, it's going to be quite hard. Okay? So, why not have this be a bigger structure, right? Why not have this be like a bigger structure, C1, and inside let's have a smaller structure, okay? Which is smaller structure. Note where your discontinuity would be in, right? Note it. Your discontinuity would be when z is equals to minus I, right? If z is equals to minus I, you'll have discontinuities. So let's have a circle which is surrounding, which has minus I at the center. A unit circle, okay? So if we were to have that unit circle and if I parameterize it, as in minus I is here, Okay, keeping this as your origin, we make a unit circle, and this unit circle is our contour. Unit circle meaning the radius is 1. So unit circles, of course, have the value of the function that e to the power I theta. Unit circle, the radius is 1. The theta varies from 0 to 2 pi, and the center minus I. This is, of course, again oriented in this manner, using the theorem that the fact that and the other preceding rules that you have to follow. C1 f of z dz is equals to C2 f of z dz. Okay, now our C2, I cleverly take my C2 to be zt is equals to minus I plus e to the power it. Now, this, if you are unaware, is basically the equation of a circle which has minus I as the center. Okay, I cleverly took this so that I can make this make the integral pretty easy, as you will see. Okay, and our t, of course, varies from 0 to 2 pi. Okay, let me do the integral. I'll erase most of these parts here. Of course, z prime of t, we have zt, z prime of t is simply I e to the power it. Okay? Since we have that, and of course, you must make sure that given this huge structure, if you want to evaluate integrals like this, where you have another contour inside this contour, you must make sure that your contour is absolutely smaller than this larger contour. Okay? It has to be smaller than this larger contour. Like if you look at the length of this rectangle, it's much smaller than the diameter of this circle. So keep in mind of that. Otherwise, you will be resulted in wrong values. Okay, so evaluating the integral again with the help of parameterization. Okay, so one upon z plus I. Z is of course minus I plus e to the power it. So minus I plus e to the power it plus I. You can cancel the i's times the derivative of z with respect to t times I e to the power it, and of course what we integrate with respect to. Okay, and of course e to the power it cancels out e to the power it, which you're left with is I, and I again is another constant, so you can take it out of the integral. You have again 0 to 2 pi dt, and of course this gives us 2 pi I again. This is a weird result, but pretty fascinating result, as in, regardless of what your discontinuities look like, up until now, I'm giving you 2 pi i's. Okay? So hopefully you learned that even with like complicated contours, you can take inside another simpler contour to integrate, so that you can find the value for the integral for the overarching contour, because of the fact that you erase it again and state it again so that you guys absolutely remember it. The fact that to evaluate the larger integral, f of z dz, the values of the larger integral, the integral over the same function with a larger contour, just take the integral, taking a smaller contour that is much easier to work around with. As we've seen here, it's pretty easy to work around with this contour rather than this contour, because it's easy to parameterize this, right? And then get the definite value for the integral. C2 f of z dz, given the fact that these things follow the rules that have been mentioned in the starting of this video. Thank you, and hope to see you again in the next video.